Folks, I am just making a set of solutions, video solutions for the trig related rates handout. So this first one says we've got a 3-meter long ladder resting against the wall of a building. So always draw the building, draw the ground. Let's draw in our ladder. It can be green. And remember that that ladder is not changing in length. That's a constant 3. Now the bottom of the ladder begins to slide away from the wall. So let's maybe label that distance x, because we know that that's going to be a variable that's changing at a constant rate of 3 meters per second. How fast is the angle theta between the bottom of the ladder and the ground changing when, I assume that that's theta equals pi over 6. So I'm going to put in my theta. Now remember, we need to list out our variables. So I have x, dx, dt, and then I have theta and d theta dt. So here, x is, we don't know, theta we know is pi over 6, d theta dt, that's what we're looking for. How fast is the angle changing? So that's going to be my question mark. dx dt I'm given. It says 3 meters per second. Take a little pause. Think about whether that's going to be a positive or a negative. It's increasing. It's sliding away from the wall. X is getting bigger, so it's a positive rate of change. Now, we want to figure out a relationship between theta and x. And I think that's probably pretty straightforward. I've got that cos theta is x over 3. So I may need this. You can solve for this right away just to kind of have it there using this relationship. But looking ahead, I think I'm actually not even going to need the x. But you could find it right now, or you could kind of wait and see if you need it and go back for it later. So I'm going to take the derivative of each side of this expression in terms of time, remembering that theta is a function and x is a function. None of these are just simple variables. So the derivative of cos theta is negative sine theta times the derivative of the theta function in terms of time with respect to time. So d theta dt, because that is a changing function. It's not just a variable. And then the derivative of x over 3, if it helps you to write that as 1/3 x, you of course can do that. The derivative of 1/3 x is just 1/3. That's why I kind of looked ahead and thought, I don't really need to find that x. But you always could, it's not wrong. But x is not just a variable, it's a function of time. So then dx dt. Subbing these all in, let's get stuff out. So I would have negative sine of pi over 6. I want to find that d theta dt. That's my variable that I'm looking for, equals 1/3 times 3. So what's the sine of pi over 6? Sine of pi over 6 is 1/2, but I have that negative sign out front, so that's negative 1/2 d theta dt equals 1. So d theta dt equals -2. And remember that that negative tells us something. That tells us that the angle is decreasing. So the angle here, which makes sense, right? If you slide that out and after some amount of time, this 3-meter long ladder is farther away, your x got bigger, then your theta gets smaller. It's decreasing. So your therefore statement should reflect your understanding of that. So therefore, the angle is decreasing. Note that it's decreasing at a rate of 2, I almost put meters per second, but it's not, it's radians per second when it's pi over 6 radians as your angle. Okay, next one. This one says a winch at the back of a stationary tow truck is used to drag a load along the ground. So if you don't know a winch, I'm going to probably do a terrible diagram here. You've got like, I'm not even going to try and draw a tow truck. That's our tow truck. A winch is like a thing that turns and it is on a chain. Wow, this is getting bad. So a winch is like a thing that rotates. It's turning and it's pulling in a chain that's dragging some load along the ground to pull something in closer. Okay, that's what's happening. So it cranks the cable in at a rate of 0.75 meters per second. At what rate is the angle between the cable and the ground, so there, changing when the angle is equal to pi over 4? Okay, the winch is 2 meters above the ground, so we know that. And here, what's changing is going to be like how much of the rope or wire or whatever, the cable, how long the cable is. The cable is getting shorter and shorter. It's getting like sucked in and turned around that, like rolling up around that winch. Okay. So I know that I have x, I have theta, and I have dx dt and d theta dt. I know that I'm looking for this when it's happening at pi over 4. I want to know how the angle is changing. So that tells me that I need to know dx dt. Now I want you to be careful with sign here. It's cranking the cable in. So the cable is getting shorter. It's cranking it in at 0.75, but we have to indicate that rate of change is happening in a negative direction. The cable is getting shorter, so the rate of change is negative there. I may or may not need x. I'm going to wait and see. So there's the stuff that I know. I need to set up an equation that relates x and theta. So I see that that's going to be a sine theta. So sine theta is 2 over x. This one's a little bit trickier. So I want, you know what, we could leave it like this. So we get 2x to the negative 1. Now I actually think I will need to find x here. So sine pi over 4 is 2 over x. Sine of pi over 4, I know that that's 1 over root 2 is 2 over x. So x is 2 root 2. And we'll put that in into the equation and get a decimal at the end, but we might as well leave it exact for now since we can. So when I take the derivative here, the derivative of sine theta is cos theta, but theta is not a variable, it's a function of time. So I have to chain rule that and multiply by d theta dt. Then here I've got negative 2x to the negative 2, but x is not just a variable, it's a function of time. So dx dt. Now I can sub in, throw in all the stuff that I know, and solve for d theta dt. So cos of pi over, cos pi over 4 d theta dt is negative 2 over 2 root 2 squared, and then dx dt is negative 0.75. So kind of mixing all of this stuff up, put this all together. Cos of pi over 4 is 1 over root 2 d theta dt. So on the top here, negative 2 times negative 0.75 is going to be positive 1.5. On the bottom, be careful here. I've got 2 squared, which is 4, and root 2 squared, which is 2. So I am going to make that into 4 times 2, which is 8. So d theta dt is, I'm going to take 1.5 divided by 8 and multiply up by that root 2 to get that onto the other side. And at this point, I'm, throwing caution to the wind, and we're just going to have a decimal, which is fine. So it's 0.265 or 0.27 is fine. And that's going to be in radians per second. Now, does it make sense that this is positive? Is this getting bigger? Yes, that makes sense. As you get closer, as this comes shorter, so if you look like time lapse later on, that's going to be closer. X will be smaller, and this thing will be closer into the truck. So the theta has gotten to be a bigger angle, and it'll keep getting like bigger and bigger as you get closer in. Yes, this is a positive rate of change. So therefore, the angle is increasing at a rate of 0.265 radians per second. Make sure you put it there for a statement. Make sure you indicate increasing or decreasing, and make sure you have units. Okay, number 3. Two sides of a triangle have lengths 8 and 15. The angle between them is increasing at a rate of 1/60 radians per second. It follows that the length of the third side is also increasing with respect to time. So use the cosine law to find that equation. That seems straightforward enough. So here we've got c squared is 8 squared plus 15 squared minus 2 times 8 times 15 times cos theta. I would want to simplify that. 8 squared and 15 squared is 289 minus 2 times 8 times 15 is 240 cos theta. Then B says find the length of C when theta is pi over 2. So 289 minus 240 times cos of pi over 2. Oh, well, cos of pi over 2 is going to be 0, and that gives us C equals 17. At what rate is the length of the third side changing when theta is pi over 2? So we know C is 17, dc dt, that's what we're looking for. My other variable that's a function of time here is theta, which we've been told is pi over 2. And then d theta dt is increasing, so positive 1/60. So we're just going to put this into our formula here. C squared is 289 minus 240 cos theta. And then we'll do the derivative of each side. So 2c is the derivative of c squared, but that's times dc dt equals 289 is gone when we do the derivative. So now I'll get negative 240. Derivative of cos is negative sine theta, but theta is a function of time. So we have to do the derivative of theta in terms of time. I guess I could clean this up a little bit, but I don't think there's too much to do. So 2 times 17 times dc dt is 240 times sine of pi over 2 times d theta dt, which is 1/60. Now sine of pi over 2 is just going to be 1, and then 240 times 1/60 is 4. So dc dt is 4 over 34. So we could put that as a decimal, like 2 over 17, or a fraction, pardon me, 0.118, and that would be in centimeters per second. So therefore, side C is increasing. Make sure you specify increasing or decreasing at 0.118 centimeters per second. So in your therefore statement, units increasing or decreasing, and specify what's happening there. Number 4, here we have the light on top of an ambulance is rotating. So it's moving kind of in a circle, and it's going along the wall of a hospital as it rotates. So if the light is situated 10 meters from the wall, so that's going to be 10 meters, how fast is the spot of light moving along the hospital wall when the spot is 3 meters from the center of the door? So like 3 there. Okay, so we want to figure out how fast this is changing. So I'm going to draw this out. I know that the ambulance is parked, so that 10 is constant. This X is changing. It's moving as the light rotates. And I'm going to put that angle. What I need to figure out is d theta dt based on this information that we're given. It says that it makes 1 revolution, so 1 full circle, which is 2 pi every 5 seconds. So this is a rate, right? It's 2 pi over 5. That's going to be the rate of change of that. So then my variables, x equals dx dt equals, we don't know. This is when x equals 3. Theta equals, and d theta dt, we do know it's 2 pi over 5 radians per second. So we could figure out theta. That would be inverse tan of 3 over 10. So that would be about, I'm going to keep a bunch of decimals here, 2915 radians. So I've got all of my pieces here, my 2 variables, my 1 rate of change, and I'm going to find the other rate of change. I'm just going to delete the picture here. So I have space to do my math. So I know the relationship here is going to be that tan theta is x over 10. I think most people feel that that's easier kind of to see like that way. Now the derivative of each side, the derivative of tan is secant squared theta. Now that's going to be a function of time, so times d theta dt equals 1 over 10. X is gone, but x is still a function of time, so dx dt. I don't have a secant button on my calculator, so I kind of want to rewrite this as d theta dt, and then it's going to be 1 over cos squared theta. And I'm going to simplify and just get rid of that 1/10 and put it up over there. Multiply both sides by 10. So there I've got 10, and d theta dt is 2 pi over 5, and then 1 over cos squared of 0.2915. So careful when you're doing that on your calculator. I would probably multiply like 10 times 2 pi divided by 5 to get a constant, and I've got like 12.566 on my calculator. Then I'm going to push divide by, and I'm going to put in brackets, again, making sure you're in radians, cos of 0.2915 bracket and then squared. So do the cos of the angle and then square it, even though we write that squared after. But I get dx dt equals about 13.7 or 13, yeah, it will round up to 13.7 meters per second. So we can squeeze in a therefore. The light is moving at 13.7 meters per second along the building. Okay, last problem here. We've got a hot air balloon. So 2 ropes are attached to a hot air balloon. The ends of the ropes are coiled around 2 long spools attached to the ground 10 meters apart, with the ropes pulled taut, and the basket resting directly between the 2 spools. Once lit, the balloon rises and both ropes uncoil at a rate of 50 centimeters per second. At what rate is the angle between the 2 ropes decreasing? So we've got our theta labeled up there at the balloon. When point P is 5√3 meters above the ground. Okay, I see like an issue here right away that I've got like 10 meters, 5√3 meters, but then 50 centimeters. I'm going to change this right away to that is 0.5 meters per second. That's going to make that a lot easier. Now I want to figure out what's changing here. What do I know? What's going to be the rates of change that I know. So I'm going to draw this. Now, I know that that 10 meters is constant. I'm going to put an X here and here. And then I'm also going to drop down like a height through the middle, because I think that that's going to have an effect, because it says what angle is the ropes decreasing when that height is 5√3 meters above the ground. So we want to figure out what's happening and what do we know. So we could figure out x at that point. So x squared at that point, if you imagine kind of like just this, like 5√3, and that would be 5, and that would be x, that I'm just taking half that base, that I could Pythagorean theorem and say that x squared is 5 squared plus 5√3 squared. And I end up getting x equals 10 meters. So this is at the point where x equals 10. Now, now I need to figure out a relationship between theta, this 10, x, and x. And to me, that looks like a cosine law. So I'm going to say that 10 squared equals x squared plus x squared minus 2 times x times cos theta. And we can kind of simplify this in probably a lot of different ways. We'd have 100 equals 2x squared minus 2x squared cos theta. We could keep this as is, and when we do the derivative, we'll have to do the product rule, or I could divide out by 2x squared on each side, which might actually be a little bit easier. I think in the written solutions, that it does actually do the product rule, so you can see this both ways. So I'm going to rewrite this as 50x to the negative 2 on the left equals 1 minus cos theta. That might be a little bit nicer to do the derivative of. And when I don't have to have something like y equals, it's actually not so bad. So we know x is 10, dx dt, that's my 0.5. And again, always give a little thought to, is this increasing or decreasing? Is it positive or negative? Because they may not say that in the question. But yes, it is going to be positive because they're unspooling that. Now, we could figure out cos theta at this point. So I could put, if I went here, and I know that that's 10, and this is 5, then 5 over 10, theta is inverse sine of 5 over 10. So from there, and that's actually just half of theta. So where sine is 1/2 is pi over 6. So that would be pi over 3 for theta. There's other ways of figuring that out. You could absolutely sub that in to your equation here and put in x equals 10 and solve for cos theta. That will work as well. And d theta dt, that's what we're looking for. So here I'm going to take the derivative of both sides. So here I've got negative 100x to the negative 3 times dx dt equals, the 1 will be gone. Derivative of cos is negative sine, but it's actually negative already, so I'll just put sine theta d theta dt. Okay, so putting all of this together, here I've got negative 100, x is 10, so it's 1 over 10 cubed, dx dt is 0.5, and sine of pi over 3 d theta dt. So if I multiply all of this stuff on the left, we've got I get negative 0.05. Sine of pi over 3 is root 3 over 2 d theta dt. I could keep going and just multiply through there, but d theta dt, I'm going to multiply by 2, divide by root 3, and I get negative 0.0577, and that's going to be in radians per second. So make sure you're writing your therefore statement using increasing or decreasing and using the units. So therefore the angle is decreasing at a rate of 0.0577. I don't include the negative because I use the word decreasing. When p equals 5 root 3 meters. And that is it for our trig related rates.